Electrons are very, very weird. It's thought of that at first we want to say, aren't electrons particles? Aren't they these little things that are negative? And yeah, there are some experiments that give us data that makes electrons look like particles, but in other experiments we get wave-like properties out of our electrons. And so in this video we're going to focus on the wave-like properties of these electrons. And to describe a wave, we need a wave function. And so the wave function is what came from Schrodinger. Schrodinger developed this wave function and said, I don't know what this means, but it's a way to take classical physics, throw it away, and say, let's give it more of a wave-like treatment. And so he created a lot of these images where we have not particles, but waves, these lines on this graph. And these graphs are actually functions. And so a function is just a machine. And in this case, we can say, well, if I have this machine and the machine is a function, I'm going to feed this machine something. I'm going to feed it x values, right? I'm going to feed it certain x values. And once I feed the function this x value, the function is going to take the x value, look at it, and it's going to give us a output. And in this case, it's going to give us whatever psi is. And so this is a relationship between x and psi that the machine, the function, is able to show the relationship between. But again, wave function, not super helpful. You will see in a previous video, we can use it to think about nodes. But what's more interesting is when we square it. So squaring a wave function brought some meaning to the wave function that's useful for chemists. Now, let's first talk about what happened. We still have waves, we still have graphs, but now, if I take this bottom part of the graph, that has a negative psi value. And if I times that negative psi value by the same negative psi value, I'm going to get a positive one, because we know negatives times negatives are positive. And so now we get a positive value. And so when we're reading a graph, we always need to know what is the axis that we're thinking about and what are the units, if any, applied to our graph. And so on this graph here, what we're going to see is that the y-axis, the psi squared, is telling us the probability of finding an electron at an x value. So we tell the machine, I'm at this x value, and the machine, the function, says, oh, I can tell you then the probability of finding an electron. Thanks to the machine, we now know where I'm likely to find an electron. But a key thing to note is this is only at a point. So I'm giving it an x value away from the center of my nucleus and saying probability of finding it at this point, and it reports it for me. But electrons and orbitals are not points, or at least they're a collection of points. So it's not very useful always to just measure probability at a point. And so the last thing we want to cover is radial distribution functions. This takes that last function, the psi squared, and by timesing it by 4 pi r squared, something interesting happens and we get this new graph over here. On this graph, we're able to look at the probability again of finding an electron, but this time it's at a surface. And the x value is again reporting how far are we away, how far is this surface that we're creating away from the nucleus. So I say, I'm here, and I tell my function, I tell my machine, hey machine, I'm this far away. I'm this far away. And the machine says, okay, you've given me an x value. Thank you for the x value. I'm going to output the value here of a probability. And that's the most likely place to find an electron. And again, this is all just functions. Every single one of these is a machine where I give it some sort of value, most helpful in the wave function squared and the radial distribution function, because we know what we're talking about. We're talking about this distance from the nucleus. And we get probability of electrons at a point or at a surface, which will be very useful as we walk further into orbitals.